like to ask additional questions afterwards, just reach out to me. I've put this website on the bottom, emlab.eng.utah.edu, and this is where I've been putting my papers, so you can download them if you like. You also can contact me through this webpage. Dear, now that I can annotate, I can't seem to make the slide move. Let's see. I need to stop annotating. Sorry about this. Yeah, because as soon as I have the annotation, it's not recognizing my screen. Okay, let's go now. Okay, there we go. So the reason that we're interested in implantable antennas is because there are so many different kinds of medical implants today. Here are just a few of the examples. There actually are more. So for example, implantable cardiac pacemakers were one of the very first medical implants. In that case, like right here, you have a pacemaker that's implanted in the muscle under the shoulder. It has a cable, literally a transmission line, that goes over and is implanted or attached to the heart. It shocks the heart using that battery to keep the heart pacing at its proper distance. But here's the important thing. This is the pacemaker today, but here's the newest pacemaker today. Look at this one over here on the right. It's implanted directly in the heart. It doesn't have the battery pack in the shoulder. It's a fully implantable pacemaker. It's smaller, better medically. It's easier to insert. So in the case on the left, you actually have to do open heart surgery. In the case on the right, you could actually just push the little pacemaker up through the vessel or the artery and implant it directly in the heart without having to do open heart surgery. Obviously, a much better medical outcome. There are other things as well. Here to the right is the artificial pancreas. That's for people that need insulin, and the insulin can be tailored to exactly the sugar level in their blood. It can sense the sugar level and then automatically decide how much insulin should be given. On the next one is the artificial cochlea, and that helps people who are profoundly deaf. In this case, a implantable device, implantable electrodes have been put in through a very, very tiny, almost hair-like structure and rolled into the cochlea so that you can receive an audible signal on the outside of the body, convert it to an electrical stimulus, stimulate each of those electrodes independently, and be able to artificially generate some rudimentary hearing. Over here on the bottom left, you'll see deep brain stimulation. This actually uses the same electrical device as the pacemaker. It uses the battery pack in the shoulder today, runs the cable up through the neck, just under the skin, and then puts in a deep brain stimulation device, literally drill a hole and put kind of a long rod-like structure into the deep part of the brain that needs to be stimulated. This is very, very effective and used today for treating Parkinson's disease and other types of epilepsies and tremors. And it's also used for depression and mental conditions, which is very important. But as you can imagine, that's a very serious surgery. Over here on the right, this is the artificial vision. This is where you can put an electrode inside the eye, be able to receive a picture outside the eye, convert it to the electrical stimulus, and then be able to make rudimentary vision. These are only a few of the medical implants, and more are coming constantly. So keeping up with the medical community is actually really challenging for those of us who are in the design community. So there are many things that currently are on the market today and more coming. So again, the important thing here is that there are many things that are pretty big on the market today, and the goal is to be able to shrink them. So you're going to see shrinking as the major theme of medical implants today. So here's an example of the Utah electrode array. You could see there are a bunch of little points on this little electrode right here, and it can be pushed into the brain or a nerve or any other place that needs to be stimulated. This is the electrode array typically used in the back of the eye, for example. It's 4 millimeters square. The electronic devices today are all wired. See how this cable's kind of coming out the bottom? That's a whole bunch of little wires that are connected to each electrode independently. Very important that they're independent in order to be able to get the sight or the brain stimulation or in fact the brain recording that we might want to do. But next generation, those wires will be replaced with a wireless device. The battery will be on the back of the implant, 4 millimeters square, and the wireless communication system will have to be there too. So the challenge is the size of this. So let's see what happens. So the most common wireless technology today is inductive coupling. It's used for two things. The most common thing is recharging the battery. As you can see, none of these have a battery that's big enough to really be able to, for example, pace the heart very long. So you'll have a coil on the pacemaker under the skin, you'll have a larger coil in a holder outside of the skin, and you'll transmit power to recharge the battery. This can also be used for rudimentary data transmission. So it's not high data rates. Certainly, this isn't a video link. It's very low rate data transmission, and there are some pretty significant challenges. Distance is the biggest. Inductive coupling, you need to have the two coils very close. Rule of thumb is that you want to have the coils close enough that they're within the diameter of the coil, so very, very close. So you can't get a lot of wireless transmission. It's only wireless through the skin. And then there's a problem of aligning the coils. The frequency and the data rates are very limited, and the efficiency is a pretty good challenge. It's hard to keep coils like this to be an efficient communication system because the magnetic fields which they generate go in all directions, and you only pick up a little of it. So you know that you're losing a lot of your transmission. But there have been improvements in the inductive link, and you'll see these throughout the electromagnetics community and still more coming. One of the first was being able to do printed inductors so that you could have many, many coils in a very small area. These are pretty good, a little bit of loss of efficiency because of loss in the printed metallic materials, but not bad. These are pretty good inductors. The one down at the bottom is making the inductors even smaller. So this is a 1 millimeter coil where it either had a C-shaped coil or a little wraparound to be able to be used for very small implants. Not a very efficient device, but a very, very tiny one. So I actually began working in this area in 1999. I had an undergraduate student, his name was Sam, and this is literally his pacemaker. He was a climber, he was very athletic. He was an undergraduate in my electromagnetics class, and he missed class for pacemaker replacement surgery. He wanted better communication with his pacemaker so that the doctor would know what was going on and he wouldn't have to go in all the time for updates. So he did his senior design project on the pacemaker and how to make it better. And here was the challenge we were facing. The frequency that's typically used for communication is 403 megahertz. It's actually 402 to 405 megahertz. So we are designing at 403. So you can see that at high frequencies, we can get, if we were able to go to higher frequencies, we can get a smaller antenna. That's good. But we also have more loss in the body. So if you just imagined a half-wave dipole, this is how large it would have to be inside the body at those frequencies. Now, this pacemaker at that time was 2 to 4 centimeters across, so a 5-centimeter antenna would almost fit, not quite. And again, the challenge is if we went to lower frequencies, it's better for going deeper into the body. We don't have as much attenuation. But if we go to higher frequencies, we can make the antenna smaller, which is what we want. So we certainly have this trade-off, this push and pull between the frequencies. And the frequency that was chosen was 402 to 405 megahertz. So these are the frequencies that can be used for telemetry or data and power communication. There are several industrial, scientific, medical bands, and these are typically what you'll use in the lab if you want to test out these antennas. So 433, 915, and 24 megahertz are the frequencies that were commonly used throughout the 1990s and into 2000 because they were available. But they still have a lot more interference because there can be many different types of technologies other than what you were designing on these frequencies. Still, if you're testing in the lab today, we would typically be using 433 because it's the closest to the band we actually want, but it's legal and easy for us to be able to do these testing. Now, a dedicated band for the Medical Implant Communications Services, MICS, as 402 to 405 megahertz was established in 1999. It was expanded to the Med Radio band in 2009, just expanded a little bit from 401 to 406 megahertz. So these are the frequencies that you need to use if you're designing medical devices. So again, we would design with these frequencies, but in the lab, we test with the closest ISM frequency. Okay, so if you're going to try to fit an antenna onto or within this battery pack, and you want it to be able to transmit significantly further than just a few centimeters, one of the first ideas was to use the planar inverted F antenna, or the PIFA. I kind of highlighted in yellow where you can see it's an upside down F. It's made from the antenna radiator, which could have many different shapes on the top. The pacemaker battery pack acts as the ground plane. Both of those are typically titanium. Then you have a feed system, which goes into and is driven by the battery that's in the pacemaker body, and a ground pin that helps make this act like a PIFA. So the planar inverted F antenna has been one of our favorite designs. And then you would typically roll this up and make something that would make this antenna work better. One of the things that you can do is use a substrate. You're going to want a substrate anyway so that your radiator doesn't short against your ground plane. And if you use a substrate with a larger epsilon r, then you're going to have a smaller antenna. So that's good, but it's also going to be a little bit less efficient. So there's a little bit of a trade-off there in the substrate material. So the next thing that you want to do is take this dipole and roll it up, make it smaller. Now, it doesn't work exactly like a dipole then. You start getting coupling between the arms or the pieces of this rolled up dipole. And you still are going to use the feed. We use a ground pin there to make the dipole act like it's twice as long as it really is. So see how there's that virtual antenna on the side? That's not exactly an antenna, but it makes this antenna radiate as if it was twice as long. So that's the concept of using the ground pin on the PIFA and rolling up the antenna. And you'll see that theme throughout many people's research. So we experimented with both serpentine and spiral antennas at the time, as others have as well. And we found that the spiral antenna worked just a little bit better. The reason it did is there's actually a little less coupling between the arms. The current is very strongest, closest to the feed, and it's a little bit weaker at the tip. And so if you put the tip of the antenna closer to the stronger part, you don't have two strong parts that are trying to couple to each other. So the spiral just tends to work a little bit better. So the other thing that you can do is you can use the location of these feed and ground pans to tune the frequency of your antenna. You don't have to slide them very much, and you can get some pretty good tuning capability. Now, the next important thing is that we're going to take this antenna and we're going to put it inside the body. The trouble with body tissue is it's really very conductive. Our bodies are mostly made out of water, and with water and salts, that's going to short circuit your antenna radiator and make it act like it's really tiny. So it makes it not even use the full antenna. So we need to do something to take care of that. Going to make our antenna effectively smaller, that's good, but it's going to short it out. So we'll use a superstrate material that is insulating. So both the substrate and the superstrate should be insulating. They insulate the tissue, they insulate the radiator from the body tissue, yet the body tissue is still able to reduce the size of the antenna. So this is the final size. This is the final basic design that you'll find in almost all of the antennas that are external to the pacemaker today. So the effect of the substrate and the superstrate materials is really quite to be expected. So as you increase the superstrate, as you increase the dielectric properties of the superstrate, your frequency will actually fall. If you increase the dielectric properties of your substrate, your frequency will also fall. And remember, we're trying to always get to the lowest possible frequency. So the higher dielectric substrates that can also be low loss are really our favorites. So there have been several people that have followed this lead. So here's another example of a spiral antenna. Here's another example of different types of ways you might put the spiral antenna together, make it fat, make it skinny. You could do serpentines. Again, here's a serpentine device, although we've typically found that the serpentine didn't work as well for transmission. Turns out it worked really well for Erdem Topsicles group as a sensor as well as a communicator. So realize that these antennas can be used for two things. They could also be used for sensors in future designs. In fact, we generally joke, if an antenna is a bad radiator, it's probably a good sensor. Now, these designs have also been done in 3D. You'll find kind of the same things. You'll see the serpentine and the spiral designs that have been twisted up and used in 3 dimensions. And in fact, notice how small the design on the right is. This is for a capsule, just a pill that you can swallow that can go through the intestinal tract. This design is very small indeed. And then there are many other shapes. One of the designs that we did was a genetic algorithm PIFA. It looks kind of random, doesn't it? It is. This is where you breed antennas. You take 2 antenna designs, you call one the father, one the mother, and you cross them. If there's copper in both places, the baby antennas will have copper, and if not, they'll have air. And if the mother and father have randomly copper and air, you'd put them together so the baby had some of both. And as you breed these through multiple generations, you actually get an antenna that's really good, works really well. You just don't understand it terribly well. It's a random looking device. So what's going to happen in the next generation is actually really important. And that's that we'll be moving away from the titanium battery pack to the much smaller 4 mm fully implantable device. It's actually technology in battery development that's enabling this, because the battery is the limiting factor in the size of the devices today. So as we get better batteries, frankly, because of the technology that's happening due to electric vehicles, as those batteries get better for vehicles, they're going to be better for implants too. So it's expected that within less than 10 years, we will have a battery that will be very functional on a 4 mm device. So the challenge with that is I could design an antenna for um, the implants we have today, but how to do it for 4 mm? We tried a lot of things. I will tell you, they don't work. So we tried making it smaller. We tried using higher dielectrics, and there are higher dielectric materials coming available, but there are some serious challenges. The laws of physics basically say that any antenna that's 4 mm in size, no matter what we make it look like, at 402 to 405 megahertz, looks like an infinitesimal dipole or an infinitesimal loop, not an efficient antenna like we want. So once you look at that and you say, actually, it's kind of impossible to make the antenna fully on the 4 mm implant, but that frees up something. If it's going to be impossible to put it all on the implant, let's not. Let's look for another place to add antennas. So the surface of the body is big. We can use the whole surface if we want to. And in fact, the body is covered with skin, and then under all of your skin is fat. And that fat is actually a semi-insulator. It's made of oil instead of strictly water. It does have some water in it, but it's a near insulator. So we can actually build antennas in the fat layer. So realize that that fat layer is there available for you to put antennas. So you can make the antennas as big as you need to. So instead of having a single antenna with a single feed pickup on the device, you can have a very tiny feed on the 4 mm device, and then you can have a re-radiating antenna in the fat layer outside, and you can make it as big and as wide, whatever size and shape you want. So this opens up an entirely different opportunity for antenna design for medical implants. We've called it a tattoo antenna, but literally the process of tattooing isn't sufficient. So we actually use injectables for this. And I can explain why in the future, but it's an antenna done in the fat layer is actually an important opportunity today for medical implants. There are a number of materials that are available for this, and more coming all the time. The biomaterials community is huge and vibrant, so watch for more materials coming. I compare all of my materials to copper tape because it's something you can make antennas out of very easily. It's about as good as it gets. Gold would be better, but copper's good enough. Copper mesh works very much like copper tape, interestingly. And then gold nanoparticle composite materials are really interesting. There are so many different polymers that are coming out today that can include materials such as gold. Gold is inert biomedically, so it's a really great conductive material to be used in the body. It's better than silvers and coppers and such. So most of the materials will actually be built with gold nanocomposites of some kind. So keep your eye on that. Now, as we tested these antennas, what we found is for us to be able to do a good antenna, it basically needed to have a conductivity that was above 10 to the 5th Siemens per meter. And there are many biomedical materials that are headed that direction. So we tried this with actually an L-coat ink. It's not biocompatible, but it was cheap and available, and it has a conductivity above 10 to the 5th. And you can see, in fact, we were able to get antennas that could be measured clear down to the 402 to 405 megahertz band that we were looking for. So we're pretty excited about that in the first test. This is a piece of meat with rat skin and the fat attached that we would then use to test our designs. We then compared copper tape and gold nanoparticle material. It was a very serendipitous opportunity where I met a young chemical engineer. He's like, I've got the material for you. And indeed he does. So it's a polymer, very soft, very thin, and also very compliant, which means that it's not going to cause damage inside the muscle because of, like being moved around. And you can see that this gold nanoparticle material worked virtually as well as copper in our designs. So we were very excited. And this is actually my current favorite material. But new materials are actually coming, and these are important to keep our eyes on. There are so many applications for implantable medical electronics that may include antennas, wires, sensors, and other things. The ability, for example, to print a sensor directly on an organ, maybe to tell if it's swelling, for example, To be able to like literally print or paint directly onto an organ is a pretty cool opportunity. But we need that material to be soft, compliant, and able to be solidified to stay in place. One of the mechanisms of doing this is very much like using epoxy. Epoxy glue takes two materials and it puts them together, and they cross-link and solidify, but only when they're mixed. In order to keep them from mixing, you could put one of those materials into nanobubbles, and then if you wanted it to mix only at a certain temperature, you could make it so that the nanobubbles broke, release the material so that they would mix at the correct temperature. So this is in fact what is done. The polymer material, it is similar to epoxy in the way that it is used. And the whole thing about designing this material is how to create the nanobubbles so that they are able to control the gelling temperature of this material. The material that we're using today gels at about 40 degrees C. 45 is where the body starts to be damaged. So we're shooting for gels between 40 to 42 degrees C. Now, that could be gelled directly by body temperature, but things tend to not heat up quickly enough, and the fluid often moves away without gelling before it's actually been solidified. So the next important thing is how we might heat that. Well, in electromagnetics, we've been using coaxial probes for heating for some time. They're used in a lot of medical applications, such as radiofrequency cardiac ablation and other types of surgeries and cauterizations. So imagine if we have a coax with a hollow center conductor where you could just inject this like a needle into the body. You could squirt out the material, heating as you go, back out the antenna. You could actually build wires within the body. You could build wires and antennas. You could build them in the fat layer, or in this picture, we're actually saying, why limit yourself to the fat layer? You actually have the ability to inject a biocompatible material any place in the body and make any type of design you want. Now here I'm showing kind of a V-shaped antenna. And this is what happens with a V-shaped antenna. If we know that in electromagnetics, things concentrate at pointy tips, they also concentrate at small gaps. So in this case, we have an antenna with both pointy tips and a small gap that's able to take the energy coming from a plane wave outside the body and concentrate it down very near the implant. We probably would not choose to make a direct connection to the implant because medically it would be likely to tear itself loose. But just having this passive connection provides up to 16 times as much power to the implant location. Thus, this works like a better antenna than we could possibly have put even on the pacemakers today. So the important thing about the future of medical implants is that they are going to be getting smaller. We as antenna designers and electrical engineers need to respond to that need, and the laws of physics just don't open up new opportunities for us. So instead, we need to think outside the box. We need to realize that we have places on the body that we can put antennas that we hadn't considered possible today. We've got the entire fat layer that's a realistic place to put an antenna. And then we also have the ability, because of new materials and new methods, to seriously consider three-dimensional antennas inside the body. I consider this 3D printing inside the body to be one of the true opportunities for medical devices in the near future. So we have a lot of medical devices today. Many, many more are already on the design table. Many are coming out on a regular basis. And you can imagine seeing many more. But the important thing will be that they will be tinier, they will have higher data rate demands, and they will be intended to be surgically implanted without surgery, so minimally invasive surgery. And that's where the next generation antennas need to go for medical implants. So I'd be glad to take just a couple of questions, and thanks so much for having me today.
Yeah, thank you very much, Dr. Cynthia Furse, ma'am. So we have some questions in the chat box. And one question is how to calculate the effect of metal corrosion on human body function?
That's a really good, important question. And it's not actually what we do in electromagnetics, but there's an entire field of biocompatibility study. Typically what they do is they'll put the metal inside a corrosive material. It's usually even more corrosive than body tissue. Think of this being done in a petri dish. And then they just leave it there for, a day or two, or a week or a month. And then you just sample the material that's around it to see if the molecules from the metal have moved away from the metal and into the surrounding material. So that's actually how you test to see if the corrosion is is going to cause trouble in the future? So that's a very good question.
Thank you, ma'am. And now we have one more question, that is, can you please explain if there is any impact of muscle movements on the implantable antenna?
Oh, on the muscle movements, absolutely. In fact, there's this really interesting factor called the Twiddle Factor. Twiddle just means moving something. Where if someone has a pacemaker under their shoulder, they may just rub it kind of inadvertently. It doesn't really hurt, but they're just sort of messing with it. You tend to. And it can actually make the pacemaker twist and twist and twist until it can break the wire off. So yes, there are significant impacts from the muscle movements. Now, if I build an antenna on the surface of the body and the body moves, does the antenna move? Absolutely. Does that affect how the antenna works? Yes, absolutely. We have to consider all of that. We have to consider the stretch factor, as for example, you might stretch your arm. You have to consider both the stretch and the bend and the possibility that you might cover it up, say by moving your shoulder over. Yes, these are all important effects that have to be taken into consideration.
Thank you. Dr. Devdeep Sarkar, you can unmute yourself and ask the question. You are a co-host now. Okay, maybe I'll ask.
Yeah, well, yes, thanks, Dr. Mahesh. So I had just one quick question. I mean, you mentioned about the typical like future devices, implantable devices will probably have higher data rates. So what are the typical values of these data rates that people are looking into?
Today, data rates are on the order of kilohertz, honestly, and megahertz is where we're kind of able to push it today. You can get up into the low megahertz. The hundreds of megahertz is pretty much going to be required in the near future. Now, the important thing about that is that may not be a continuous requirement. So in many cases, we don't expect the data to be sent from the body continuously, although that is kind of the dream, is to be able to, for example, be reading all of the information about the electrical activity on the heart or whatever other organ you're testing or implanting, to be able to read that, send it to, say, a hip-mounted device, and then be able to have that go from the cell phone straight to the doctor. If you had that, you honestly would be able to predict cardiac arrest so much earlier that you could just call the person up and say, your heart's not doing so well, come on into the hospital, we want to help you out. So that's the ideal application. It's not going to be there even in the next generation. And so the data rate up and down links will probably still be intermittent, like when you are close enough to the receiving device, but hundreds of megahertz for certain.
Megahertz, okay, thanks. Thanks.
Yeah, thank you.
If I can ask one small question, I guess.
Yes, sir. Please go ahead, sir. Please go ahead.
Very nice presentations, and I enjoyed all this development that you presented. One question, I think it's also someone else also asked in the chart, is how do you balance between the transmissivity of the electromagnetic waves versus the SAR, right? Safety issues. So that seems to be the major obstacle in getting these things into the body. Just your comments, I guess.
SAR is specific absorption rate, and that is how much energy is deposited in a particular small region of the body. The two guidelines are typically 1 gram, which is about 1 centimeter squared, and 10 grams, which is a little bit bigger. So the important thing is to realize that SAR being a very localized measurement, we need to be sure that we don't have high localized SAR. So as soon as you've spread, so you're going to get localized SAR near the feed point of any antenna that you have. So you're going to want to keep that away from the body tissue. The substrate and superstrate is very important. So we'd love to have a thin superstrate, and frankly, electrically we could, but we need to use a thicker superstrate so that the fields at the feed point have spread out before they actually hit the body tissue. And that basically makes the power less dense. So it's power density that we're always trying to minimize. So you really do have to insulate the feed areas of the antenna to keep them physically away from the parts of the body that you don't want to impact. The other thing that is likely to happen with the safety guidelines, with the SAR guidelines, is that it's very possible there can be adaptations of those for medical applications. So for example, are we as concerned about SAR in the shoulder as we might be in the brain? The answer is probably not. So those may get adapted in the foreseeable future to enable some of this. Now, the place that you're going to see your highest density is going to be near the feed point that's attached to the battery. The tattoo antenna that's on the outside isn't actually going to have a feed. It's going to be a pickup at the outside, and it's going to have much less density of power. So it's going to be this 4mm battery pack that's transmitting out that will be your limiting factor. So probably the thing that's going to be the biggest limit there is how thin can we make the insulation around it. It starts out 4mm cube. If we end up making that a full centimeter cube because we have to use insulation, that's never going to fly. So using higher dielectric materials and insulating the feed point is really where that's going to be at, and that will minimize the SAR.
Yeah, this is going to be an additional constraint on the antenna design while they're doing for implantable applications,
Yes.
I suppose. Yeah. Thank you very
Yes,
much.
absolutely. Yes.
Yeah.
Yeah, Mahesh, I'm having one question.
Yes, sir. Please, go ahead.
Yeah. So thank you, Professor Cynthia, for wonderful presentation. I just wanted to know whether any standardization work is going on, because we should have some limit from human safety point of view, what can be the maximum input power as well as what can be the maximum output power from the antenna. Whether any work is going on or any recommendations are there?
Yes, actually, there are already standards for the amount of power that can be transmitted and received. It really is, as CJ was mentioning, the SAR guideline, which already exists. So the IEEE C95.1 standards organization originally recommended a standard it was about 1999. It was actually adopted by the American Federal FCC in the US, and then it was picked up throughout Europe and then internationally as well. So there are the two guidelines, and each country uses one guideline or the other. One is based on that 1 gram SAR, the other is based on the 10 gram SAR. Although there are also total power limits, they don't end up being the effective limits for implants. It is this localized SAR guideline that ends up being the effective limit. And so yes, this is already law in virtually all countries, including India. India, I believe, uses the 10 gram guideline. But yes, it's the SAR guideline that limits the amount of power that we can transmit.
Thank you.
Great.
Yeah, thank you. We have a question on can we know what is the way we embed the implantable? The techniques.
So today it's done surgically. Right, they literally cut a hole, they put the battery pack in, they run the cable, more holes. So it's a very serious surgery. Replacing the battery pack just in the shoulder under the muscle, not as serious a surgery. Cutting muscle isn't as dangerous as cutting an organ. But basically today it's done surgically. The next generation, and you're starting to see that already with the very small, the miniature implant going into the heart, is to use what they call minimally invasive surgery. And typically that's where you'll go up through a vein or an artery. The major vein comes in through your groin, right there by your thigh, and they can make a cut there, and they can actually inject things that are pretty big, and they can use cables. It's literally long, like 3 or 4 foot cables. They can push those through the arteries and veins and steer them into any place that you have a venous system within your body. So you can push it up and into the heart, you can push it up and into the brain. That's how aneurysms are fixed with medical stents. You can push it down the arm, down the leg, over to all the major organs. So that's the goal for the minimally invasive surgery, is to basically follow the veins, the veins and arteries, and be able to place the medical devices any place that you can get to through a vein or an artery, which is fortunately most of your body.
Yeah, I have another question, Professor Cynthia. I just wanted to know, with respect to simulation, when we implant the antenna and when we do really measurements, so how much closeness or how much variation we have observed?
Way too much. So the simulations, of course, there are many different ways of doing simulations, FDTD, method of moments, all of that. There are commercial codes. We're all using commercial codes mostly at this point because they're so much easier to, for the students to learn. So yes, you can do simulations and they're great. And we know a lot about biological tissues. We can include that data. And then when we actually go and build it, it's always different. If you get within 10%, that's brilliant. It's not, I mean, even if you get within the same order of magnitude, that's often considered pretty good. So yeah, there's a pretty substantial variation in all biological simulations to the measurements, much more so than you'll find in other types of building devices. And one of the major reasons for that, we are actually now quite certain, is because although we think we know the electrical properties of human tissue, it varies so much from individual to individual. Even within your own shoulder muscle, there'll be some pretty substantial variation. And so if we include that in our simulations, which our group is actually now including that, you'll just find huge detuning effects on these antennas. So we have to actually include that. It's not really included in our simulations well today, but if you were to include all of the biological variability that you expect in both size and electrical properties, then you'll find that your antennas do fall within those ranges really well. If you do a single one, you're always off. So yeah, variability simulations would be really important.
Yeah, we can expect same kind of variations. So just another sub question on the main question: how much margin do one should have when because anyway we will be doing some simulations and we will be optimizing the results, and then when we are really implanting the antenna, or we can tell that will be a kind of fabrication in a layman's language. So how much margin one should have so that at least the desired results one should get after implantation?
Yeah, so if we are just looking at margin, we probably aren't going to be assessing that very well. We really need to be looking at the variability. And so in fact, a talk that I'm not giving here, but that I'd be glad to come and talk to you further about, is being able to simulate variability. So there are some new efficient methods of being able to put in the full variation that you expect in electrical properties and actually include that. So it will tell you what the variability in your SAR is, for example. We could also do variability in S11. You could also include the physical variability, like how much the things are likely to change in size or shape, and be able to include all of that. So you really do need to evaluate this variability. It's not something we're doing today. It's not mainstream. It's not the standard, but I think it needs to become the standard. So just designing with a margin, I don't think is good enough. I think we really do need to consider the variability, and then we'll know what our margins are for our designs. So I'd be glad to come and talk to your group sometime about simulating variability, but it's a really important problem, and I don't actually think we're doing it right today on average.
Yeah. Thank you very much. We will again invite you for the next session, definitely.
Okay, please do. Thanks so much. I know I've taken more than my question time. I invite you. I don't see how to type into chat. Why don't you just put my email in chat, and people are welcome to contact me.
I'll
oh, actually, here's my email on my slide. My email's right there on the slide. Further questions, just get hold of me.
Hey, great talk, Cynthia.
Thank you.
I think I learned something today. I think it's very useful talk, and I have a question though. The one inverted F antenna you showed, inverted F is or PFA is generally very wideband. It can give you more than octave bandwidth, I believe. And then you're using for narrowband application like 403 to 405 megahertz or something. So if there are other pacemakers working at a different frequency band, how do you stop the interference between the different pacemakers units? So maybe one could be for the heart, one could be for something else. So is there any interaction between the pacemakers, and how do you avoid that?
That's a super good question. So the whole bandwidth question is a pretty big deal. You want broader bandwidth so you have higher data rate, but yet you want narrower bandwidth so that you don't have as much interference. And mostly you have to be sure that your bandwidth is within the mix band, now 401 to 406 megahertz, because if you're outside of that, you're going to have other types of interference as well. But if you actually look at the bandwidths that we have for these antennas, I'm just going to pull up one right here, for example. it's not that broadband. The body immediately starts to narrow the band of this, the conductive materials around it. So it's not really a broadband antenna by the time it's been applied. So the body helps to narrow that. That's one thing. The body kind of filters as well. And then, of course, the devices that are used, the electronics, can filter this even further. Your antenna is not your only filter, although you want it to be a decent filter so you're not bringing in too much noise.
So is that the properties of the skin or muscle, etc.,
Yeah.
frequency dependent highly?
They are mildly frequency dependent, but just having the lossy material around this antenna reduces its broadbandedness.
Okay.
The way I often explain how to make an antenna more broadband, when we're just talking about this in antennas in general, is you want to have multiple paths for your current so that you can have a short path for high frequency and a long path for low frequency. And in this case, one way that it can become broader band is by reverberating back and forth. But the lossy materials reduce that reverberation, damp it substantially, so you don't get the same bandwidth for these antennas that you would in air. The body itself just dampens those out.
Yeah, that's a question. I think I understand now. We are making one inverted F for covering 10 gigahertz to 30 gigahertz. That's for different applications. That's for military application, but that's why I was wondering, because that's an air propagation.
Right.
So it's not an issue, but in this case, probably because of the body, I think you might get some frequency dependent response.
Well, for your amusement, if you're simulating that, just put some conductivity into the material, like the air material around that. Just make epsilon R2 and conductivity, I don't know, something, and you'll immediately see, you'll kill your bandwidth.
Yeah, thanks, Cindy. Yeah, I understand now.
Okay, thank you.
Great.
Good questions.
Yeah, thank you very much, ma'am. And we are very grateful to you for your great talk on implantable antennas. And as our chair-elect Puneet Mishra said, we'll be inviting you for further talks also. And thank you for joining us today. And thank you, Sudhakar Rao sir. Thank you, Puneet Mishra sir. Thank you, Reddy sir, and all other eminents who have joined today. Thank you very much, madam.
Thank you. I hope I meet you in person soon.
Yeah. Thank you. Bye-bye.
Bye-bye.